Okay, it's working, right? Okay. Okay, welcome everyone to our weekly seminar series. Today's speaker is our own, it's working, yeah. Sangwan Liu, I hope I pronounced it correctly.
Perfect.
More or less. Okay,
Yeah.
Thank you so much for lying. Thank you very much for lying. It was really good. Okay, and today is going to present a very interesting work that's been published very recently in Nature Communications with the collaboration of Rosa, Urens, and David. So something that actually is full, let's say 100% IFISC product, let's say.
Yeah, exactly.
So, okay. So, and before joining IFISC in 2019, Sangwan just got a bachelor degree and a PhD in physics from the Korean Advanced Institute of Science and Technology. That is actually one of the Korea's top research institutions, and also spent there another couple of years as a postdoc.
Yep.
And so the title of the talk is Beating Carnot Efficiency with Periodic Driven Chiral Conductors. And thank you so much for agreeing in giving this talk, and the floor is yours.
Thank you for the introduction. Yeah, so in this talk, I will talk about the work that I collaborated with the researchers here. It was a wonderful collaboration. So yeah, it's about quantum heat engines and quantum thermodynamics. And so it's about heat engines, which are everywhere, like from the engines of the cars or motorcycle, or in the air conditioner now. I mean, that's a refrigerator anyway. And those devices are essentially nowadays in the industry or for our society. And those are the devices in general convert heat to useful work. So every device can fit into this scheme that there is a hot thermal bath and cold thermal bath. And there is some working fluid or working substance, for example, like gas in the piston in traditional engines, connected to the both baths and observe heat from the hot bath and dump part of it to the cold bath. And the difference can be extracted to the useful work, doing work to external object. And it's kind of engineering perspective, but the question was like, what is the fundamental limit for efficiency of this class of heat engines? But as you may know well, this was intimately related to the laws of thermodynamics. So for classical systems, for example, when the working substance is a gas made of a lot of particles in the piston, then we already know well that the fundamental limit is the Carnot efficiency, the upper bound. And this is good because it's a universal value, only determined by the two temperatures of the cold bath and the hot bath. In a universal, it's universal in the sense that this does not depend on the details of the operating protocol, like how you expand the gas in time or you compress, like whatever the protocol, this is universal upper bound. But if you remind, this is the consequence of the three things. First law of thermodynamics, that there should be energy conservation. So any work extracted should come from the total heat observed from all the reservoirs. I mean, for one cycle, there cannot be energy accumulation in the working substance, or for steady states. And also, second law, over time, entropy production should only increase or stay the same. Yeah, but also it's consequence of the Clausius relation, identifying the entropy production as form of the heat. So here, this is the heat observed from the sum of the heat observed from the each bath divided by each temperature. So, but like as all the physicists were doing recently, they also considered miniaturization of these heat engines into micro scale or nano scale. And then that motivated a lot statistical thermodynamics, as you are already experts. So in these systems, in the small engines, the fluctuations become important. So we could reformulate the entropy production in terms of the stochastic trajectory of the system. And then it's just average value of the ratio between the forward trajectory and backward trajectory. And as average, it should always increase or remain same. But this is like just written in terms of the probability of the stochastic path. So to relate this to the thermodynamics, we need to relate this probability to the energies or heat. And here the linking part is the local utility balance, which states that the rate of the forward process with respect to the backward process should be determined by the heat observed from the bath, which induces this transition divided by the temperature. So when you use this, we can derive that the entropy production is made of two parts: the change of the entropy of the system and the entropy flow coming from the bath, which is in form of the Clausius relation. That's just the sum of the heat flow coming from the baths divided by their temperatures. And this local utility balance is valid under the assumption that now what we have for the thermal reservoirs are ideal. I mean, there's a time scale separation. So the time scale for the relaxation in thermal reservoir is way more faster than the time scale of the system. And the other assumption, which is not that much explicitly stated, but in my view, is weak coupling between the bath and the reservoir, because it also requires good distinction between the reservoir and the system. Yeah, but I'm not expert, so you may correct me. Yeah. So in the fields of quantum thermodynamics, now I will talk about some pioneering work in that field. And that was initiated by the question, what if the bath is some quantum object? Then the Scully and others showed that efficiency now of the heat engine can be beyond the Carnot limit. And let me review the work a little bit. So now, as all the engines, we have two reservoirs, hot and cold. And we have a working substance. And the working substance is now the photons, which are caught between the cavity, in the cavity formed by the two mirrors here. So the work is done by when the piston expands. Yeah. And if you remind the cycle of the classical Carnot engine, then it's made up of 4 strokes. So 2 isotherm stroke, which observe heat or dump heat, and adiabatic expansion and adiabatic compression. So for example, let's say we start here. So in here, we contact the photons, the cavity, to the bath. I mean, the bath now is atoms, which is in thermal equilibrium with this hot temperature. And atomic beam goes through this photonic cavity. So when you are flowing the atoms through, then this working substance is connected to the hot thermal bath. So the photons thermalize to the hot temperature, and then you disconnect them, and you adiabatically expand. Here, you adiabatically expand as doing the work by the piston to external object, and then doing that, the temperature of the photons should decrease, and then you connect to the cold reservoir, and you dump some additional heat to the cold reservoir, and then you disconnect it again, and then you compress it to go to the initial point to enclose one cycle. So because this is reversible in each time stage, this kind of cycle gives entropy production to be 0. So it realizes engine with the Carnot efficiency. But I was talking about the classical case up to now. So what if these atoms which makes the hot thermal reservoir have some coherence? What if? So as I should have explained that how interaction is between the photons and the atoms. So again, sorry, for the classical case, for example, when the atoms in the state, hot atoms emits photon by spontaneous emission, or it can absorb photons. That's how the photons and the atoms interact. So when there is no coherence in the classical engine, you can show that the efficiency is Carnot efficiency. But they could show that if there is a coherence here, which they call phasonium, and the coherence is here. I mean, now the atoms are made of the 3 levels instead of 2 levels, and the lower 2 levels are nearly degenerate. And the occupations of these levels are determined by the temperature. I mean, by the Maxwell-Boltzmann factor. Then here, if there's a coherence between these 2 low degenerate levels, I mean, if you can prepare the atom in the coherence superposition between B and C, and they could show the spontaneous absorption to the excited states depends now on the interference between 2 passes from B to A and C to A. So if you prepare the phase between the superposition in a certain way, then you can realize the constructive interference, I mean, yeah, or destructive interference. So if you prepare destructive interference, then what happens is that now there is less likely that the atoms goes to spontaneous absorption than the spontaneous emission. So in this way, interference violates local detail balance between this absorption process and the emission process. And that's the origin of how could efficiency could go beyond the Carnot efficiency. So for example, if you set the 2 temperatures equally, then still it can work as a heat engine, violating Kelvin-Planck's statement of the second law. And in their paper, they concluded that so in these devices, the coherence plays some kind of role over sorting action. So by coherence and the interference, somehow hot electrons rather emits photons than observing photons. So some kind of sorting action. So our motivation was that then what is the effect when the quantum bath is driven by AC voltage? Because we have a background in the nano electronic devices, and we know that the AC voltage is powerful tool. For example, recently there has been developed a lot of single electron sources, which works in a remarkably on-demand fashion. So single electron sources are analogous to the single photon sources in optics, and here is an example of such device. So you have a quantum conductor, for example, here being one-dimensional. And there are Fermi seas in this device. And you have a contact, electronic contact, and if you apply some AC voltage to one contact, then you generally excite a lot of electrons and holes. But there was a study that if you use certain voltage shape, for example, Lorentzian pulse, then you can excite only one electron for each pulse. So here the cones is a clean one electron excitation induced by this one pulse. And if the these excitations does not relaxes into thermal equilibrium in certain length scale, and experimentally they have shown that these theoretical expectations are valid, are correct by measuring the excitations by doing quantum tomography, which is also analogous to the tomography, homodyne tomography scheme in the optics. And these singleton devices have shown many impacts in a lot of fields. For example, in metrology. So these devices sometimes works very accurately. So for each period, they could transfer one electron without failing with accuracy below parts per million or something like that. So there are movements trying to redefine electric current standards, ampere, using these devices. And second, in quantum information, you can generate flying qubits if you encode some quantum information to these flying itinerant electrons, for example, in the degree of freedom of spins. And also in the quantum electron optics, which probes the wave natures of electrons, for example, doing interferometry, Mach-Zehnder interferometry, or Homo-Mandel collisions, Humphrey-Brown trees, so on. However, in these devices, in these studies, clarifying heat current, energy current, or entropy production are only of recent interest, which are relevant to the issues of the quantum thermodynamics. So I would like to mention that in these nano devices, we need scattering theory. So again, in the traditional devices, for example, heat engines, the device is so large, so each local part of the device is within the scale of the thermalization. So each parts are in local equilibrium, so you can apply Boltzmann transport theory. But in the quantum devices, as I explained you before, scale of thermalization can be larger than the size of the device, for example, the quantum dot. So the device can be in non-equilibrium easily, and we need to express the current, energy current, heat, using the scattering theory. So in our work, we show that there is indeed a class of quantum devices with efficiencies beyond the Kernel limits. And these were thanks to two factors, AC driving, which induce violation of the Clausius relation by inducing strong non-equilibrium, and chirality, it was unexpected factor. And the role of this, I will explain more in detail. And this may seem like second law is violated, but not, because we show that when we adopt Shannon entropy flow as entropy production, this value was always non-negative. So let me explain the setup of work. So actually, if you think simplest form of the heat engines in nanoelectronical devices is thermoelectrics. So our system is like this. you have a hot bath made of fermions, cold bath made of fermions, and in the middle you have a scatterer through which the transmission probability depends on the energy. So for example, for a quantum dot, you have a resonances of the transmission probability. And it's simple because whenever you have a electron hole asymmetry in the transmission, then you can generate power. Because, so for example, in the hot reservoir, you have electron excitations above the Fermi level and hole excitation below the Fermi level. And if the transmission to the cold reservoir is asymmetric due to this scatterer, then you generate thermoelectric current, the current by temperature difference. And if you apply a small bias, the voltage bias between the two reservoirs, but against the direction of the flow, then you generate power because it can be used to external circuit generating the power. And then the efficiency of this device is determined by the electronic power generated divided by the heat observed from the hot reservoir. So now we consider AC voltage driving to hot bath. Then actually it is easy to see that this AC driving enhances the thermoelectric current because we can dynamically enhance electron hole asymmetry. For example, like that I showed you in the example of the single electron sources. If you apply Lorentzian voltage, then only electrons are excited. So you are inducing electron hole asymmetry dynamically. So in those cases, thermoelectric current are enhanced. But we found out that AC field in this way, I mean, generally injects power to the electrons. And the electrons here are the working substance of the engines. And this makes sense because if you think Joule's law, at each time, the AC voltage should inject power proportionally to the conductance and the square of the voltage bias at each time. So in average, this quantity should be positive value. And we also confirmed it in the case of slow driving frequency in our theory. We confirmed this. So actually, this factor, the input power, hinders the efficiency enhancement due to this enhanced thermal current because now the efficiency should be redefined considering this input power in the numerator of the gain of the efficiency, right? But our key finding was that if you use some specific AC voltage, some selective AC voltage, then we could show that this input power completely vanishes. And this was a key factor for enhancement of the efficiency beyond Carnot and so on. And what I mean by the selective AC voltage is that AC voltage is applied to the electrons which in certain direction, which are going to into the scatterer, not to the electrons going into the opposite direction. So again, roughly speaking, for me, it's like it looks like a kind of sorting action that I talked in the example of the Scully, example of the Carnot engine, quantum Carnot engine. And this scheme can be realized, this selective AC voltage can be realized when using a chiral conductor in the solid state devices. For example, in the semiconductors, if you apply a strong magnetic field, then you know that it goes into the quantum Hall regime. And in that system, the electrons propagates only through the edges in a chiral way. So along these edges of the samples, shown by the black arrow. And if you realize the hot reservoir by two contacts, electronic contacts, and if you apply the AC voltage to one of the contacts, then you kind of realize this selective AC driving. So now when the electrons goes out of this reservoir, they are in non-equilibrium states. Even if deep in the reservoir, they have a well-defined temperatures and the chemical potentials. So we used Floquet scattering matrix formalism to determine the currents and power. As I told you, we need scattering formalism in this type of quantum conductors. And now we are applying AC voltage, so we should express the effect by the AC voltage, I mean the photon absorption and the emission. And they could be treated using the Floquet scattering matrix. So for example, this part is a little bit detailed, so let me be brief. So for example, to describe the transmission from the left reservoir to the right reservoir with some number of photon absorption given by this AC source is described by this amplitude AN, where the N is the number of photon observed. And AN is simply determined by additional dynamical phase gain obtained by this AC voltage. And its Fourier effect factor determines the amplitude. So actually, it's quite easy to obtain this quantity AN. So by observing N photons, the initial energy from E now becomes new energy, which can increase when the photon is observed. So the transmission amplitude is now determined by the amplitude of observing photons multiplied by the transmission through this scatterer. But now the amplitude for such transmission is determined by transmission in the static case, but with the new energy after observing photons. And due to the chirality, if we consider the events coming from right reservoir to left reservoir, it's just determined by the static case, the transmission in the static case. So here, these quantities are what we are referring to as Floquet scattering matrix. Sorry, again, another detail, but yeah, when we have a Floquet scattering matrix, then this determines the current. But I mean the current here as a time average values. In this work, we didn't consider about time resolved currents, only the time average values, because that's what defines the efficiency, right? So, for example, the energy current is determined by first, if you consider that the energy current from the electrons coming from the left reservoir, then we consider the occupation factor from the left reservoir having energy E, which is just Fermi distribution, and the amplitude going from left reservoir to right reservoir with observing some number of photons. And that probability is determined by this Floquet scattering matrix. And then that contributes to the energy current by quantity or after observing photons, right? And there are another contribution from the electrons coming from the other reservoir, the reservoir at the right side. And the heat then now is determined by this energy current, but we should subtract the energy in a useful form. I mean, which can generate the flow, the power. And the generated power, again, is just summation of the increase of the energy in the useful form, in the chemical form, if you wish. And we show that it satisfies the first law of thermodynamics. I mean, the power generation comes from total heat absorption from all the reservoirs. So about the results, I will now show our results. We considered the AC voltage in the form of Lorentzian pulses, which is known to generate levitons in the studies of single electron sources. And for the scatterer, we consider the single resonance level, which can be prepared by the quantum dots. And the colors are the efficiency divided by the Carnot efficiency. And y-axis is the frequency of the AC voltage, omega, and x-axis is the chemical potential of the reservoirs. And small chemical potential difference between the reservoirs are chosen to generate maximum power. Then the first observation was that such AC driving can realize photo-assisted thermoelectric engine. And what I mean by that is that even the system doesn't work as the engine in the static case. Whenever we turn on the AC, it starts to work as a heat engine. So here, along this line, when the chemical potential aligns with the single resonance level, this efficiency is 0 because there is an electron-hole symmetry in the transmission, because this point of 0 is the case when the chemical potential is aligned with the resonance level. So this electron part and the hole part has a symmetry in the transmission. So it does not generate thermoelectric current. But when we turn on the AC, then at the same parameter, it starts to have some efficiency, finite efficiency, generating the power. And that's because due to this Lorentzian shaped voltage, I mean the levitons, then it dynamically generates electron hole asymmetry, as you can see here in the asymmetry of the transmission function. But yeah, this was the first observation, but more remarkably, the efficiency in the AC driven case, when the frequency is fast beyond the adiabatic regime below here, then the efficiency can even be larger than the Carnot limit indicated by these dark red colors. And this was always accompanied by the negativity of the entropy production, assuming the Clausius relation, which is indicated by blue colors here. So always happens together. So this seems like a violation of the second law of thermodynamics, but the seeming violation is resolved when we adopt another form of entropy production. And actually, in previous works by Frontal and Arachea, they showed that in the quantum conductors driven by AC driving, the Clausius relation can be violated, so you should adopt this formula, which is nothing but channel entry flow. I mean, here, the sigma is the binary channel entropy function, and the arguments here are the distribution of electron going into the scatterer or outgoing from the scatterer. So this becomes 0 whenever at energy E, the electron is certainly filled or certainly not filled, and otherwise it becomes finite quantity. And we just sum up for each contribution. And we show that when you use this quantity, this quantity was always non-negative. So we kind of saved the second law of thermodynamics. And here the outgoing distribution is determined by Floquet scattering matrix. So we could calculate everything just using the Floquet scattering matrix that I showed you. So, and then the deviation of the entropy, channel entropy flow from the Clausius relation quantifies the non-equivalent effect induced by AC. So here, as you increase the frequency, this deviation grows. And this inset shows the limit of the slow driving. The deviation is determined by this quantity, which is just a time average of the scale of the AC voltage. And this quantity is related to the energy uncertainty of the electrons induced by AC driving. And it's just determined by how much the AC voltage has a fluctuation. So it makes sense. And now the positivity of this new entropy production quantity, the channel entropy flow, provides new upper bound for the efficiency rather than the Carnot value, which we show here. And this upper bound now can grow as we increase the AC frequency. And this is not universal, unlike to the Carnot efficiency. So in a sense, it's bad, but in a sense, it's good because we can tailor large efficiency using protocol of the AC voltage. And but this efficiency should be up to 1 because of the energy conservation. And there's an open question to us that then these are the real value and these are the bounds. And when these bounds are achieved is still open question for us. And as a final result of our work, even in the simple case that all the bath has the same temperature, we could generate power. And it's like a violation of the second law by Kelvin and Planck's statement, right? But this was also possible due to the violation, I mean the deviation of the entropy production from the Clausius relation. And now that deviation gives upper bound to the power generation as shown here. And the interpretation can be that the AC voltage enhance effective temperature. So when we apply even if we started from the thermal reservoir having same temperature, when we apply the AC voltage to one reservoir, then by injecting energy uncertainty by AC, the Fermi distribution now becomes a broader distribution, which we can interpret as increase of the effective temperature. So it's like now we have an effectively hot reservoir and it generates a thermoelectric current, which can generate power. And as an alternative interpretation, AC voltage kind of rearranges the electrons in more uncertain way, but in the energy distribution, because we are injecting fluctuation from the AC voltage. But this AC voltage now does not inject any network to the electrons over one period. So it's actually analogous to the non-equilibrium demon suggested by Rafael Sanchez and Robert Whitney in this paper. Like some demon, now it's not Maxwell demon, but it's some demon which just rearranges the distribution of the system without injecting particles or without injecting energy, but you kind of inject only the entropy. And that violates Clausius relation because of the non-equilibriumness. And they could show the efficiency beyond Carnot. But a merit of our system is that we do not need any fine tuning for satisfying the demon condition. I mean the demon condition that there should be no energy injection in average. Because as I showed you, our conclusion of the zero input power is valid for any form of the AC voltage. It just depends on the selective AC voltage using the chiral conductor. And yeah, I will mention a little more open questions and I will conclude. So our questions is that then this AC voltage can generating coherence. I mean, so when the electron had a certain energy in the form of plane wave, by AC voltage, it becomes superpositions of different energy states. And these are in superposition having relative phases. And actually, in quantum thermodynamics, it's an open question that what is the role of the coherence in the quantum heat engines. And in previous work by Jenin, that this coherence are known to reduce current fluctuations. So actually, we are continuing our work that then this coherence can contribute to a more stable heat engine by having less power fluctuation. I think it's very interesting direction. And there are more questions in more broad sense. So for example, what if we have entanglement in the working substance? And actually we have a paper related done by with the Rosa and Raul, which is also published recently. And what is effect of this quantumness in the heat engine, like a coherence or entanglement, to other functionalities more than just efficiency. For example, in the classical heat engines, they are known to have some trade-off relations between power and efficiency because, for example, for the Carnot efficiency, to achieve high efficiency, you need reversible engines, so everything is slow, which means you generate less power. So there is a trade-off between power and efficiency. Or there is also trade-off between fluctuation of power and the efficiency, which is related to the thermodynamic uncertainty relation. And if we twist our interest, rather than generating power doing some useful quantum computational task, then the question is, what are the fundamental bounds for energetic costs or heat dissipations to achieve certain quantum computational tasks? And as a conclusion, we showed a kind of class of the quantum devices. I mean, the AC-driven chiral conductor, which shows the efficiency beyond the Kernel limit. And it seemed like there was a violation of the second law, but it was because the Clausius relation was deviated due to the non-equilibrium effect. And here, the chiral transport was crucial. So for example, if we just use non-chiral conductor, you could never observe efficiency beyond Kernel limit because there was a large input power to the electrons, which diminishes the generated power. And we also expect experimental realizations because the regimes are approachable, and so the communities of the single electron sources, we expect that they can really do the experiments. So yeah, thank you for your attention.
Okay, thank you so much, Sangwan, for the very interesting talk, and also for saving the second law of thermodynamics.
Yeah.
So, okay, let's start with the questions, both here and online. If you are online, just unmute yourself and say something. As usual, let me encourage, let's say, PhD students to start with the first question. I don't see many PhD students here in the room, but let's see if someone, let's say one, wants to start. So just, I'm gonna give you something like 5 seconds. Otherwise, we're gonna kick you out of the PhD program. So 2, 3, 4, okay. So any questions from the general audience, let's say? Is someone? Okay, let's start from here. If you are from online, just let me know. Okay, let's start with Lalo here.
Thank you for the interesting talk. So I was working in a very similar setup when I was doing my PhD, which is the case of squeezed thermal reservoirs. Those are also kind of reservoirs that have coherence, and then you can also break the Carnot efficiency and derive other bounds and so on. But my comment,
which reservoir? Can you repeat?
Squeezed reservoirs.
Okay.
There are reservoirs in quantum optics that bear some squeezing, and then they have coherence. So my comment is, however, that so I think we already know that Carnot efficiency only applies to systems or to machines that work exclusively between thermal reservoirs, right? And this is also true for classical engines as well. So you have a classical engine where you have some input work, you are not bounded anymore by Carnot efficiency. For example, if you have some non-conservative forces inside your system or things like that, then you will not necessarily respect Carnot. And I have also another comment, which is when you identify the heat in the engine. So I saw that your expression there, which seems to be the expression that is usually what is usually employed for thermal reservoirs, right? For reservoirs that are thermal and exchange particles. So thermals that are in the grand canonical ensemble. But I was wondering whether this expression for the heat is correct here, because since your reservoir is driven by this AC voltage, I would expect that it will not be anymore in the grand canonical state. So, and this is perhaps related to the fact that you get violations of the second law.
Yeah. Great question. Thank you. Yeah. So for the first question, yeah, it's true that if you are like injecting some power which converts to the output power, then obviously it can violate Carnot efficiency. But there is no hidden power injection as far as we are concerned. I mean, that's our key factor, that input power by the AC vanishes completely. So efficiency now is, yeah.
Yeah, this I understood that you
Yeah.
subtract this, but nevertheless, I think that the Carnot efficiency can be violated in general when in cases where.
Yeah, but yeah, the Carnot efficiency was already also violated in this example, right?
Yeah,
And
but
also
even
when you use
in
the
classical,
system.
I think even in classical.
Yeah, exactly.
systems.
Yeah, it doesn't have to be quantum. Like if you have a strong non-equilibrium, then you can go beyond the Carnot efficiency. Yeah. And for the second question, first, actually our conclusion, there is a version of our result which does not depend on the heat. You know, I mean, so for our last result of the power generation from the isothermal bath, in this case, we don't have to define heat. We just show that initially there are isothermal heat baths, but we generate power. So it's already, we are showing violation of the Kelvin-Planck statement without defining heat.
You don't define heat to define the efficiency.
I mean, here there's no efficiency. There's just generated power. I mean, according to the Kelvin-Planck statement, we cannot generate power from the isothermal bath, single thermal bath. But we are showing that it's possible if you apply AC voltage. And secondly, about, sorry, yeah.
No, I didn't get it very well. But so I mean the reservoir. So do you? What is the state of the reservoir? Do you know? Have you calculated that, or have you any clue of what is?
Here, reservoir is just having Fermi-Dirac distribution. Yeah. So deep in the contact, we assume that electrons are in Fermi-Dirac distribution, okay, which have this shape. So for example, originally, sorry for confusion, but you can just focus on the one color for green color maybe. And the dashed line is the Fermi-Dirac distribution without applying AC. But if we apply AC, then this distribution deviates from the Fermi distribution with a more broadening. So it's actually something like AC.
I'm sorry, the effect of the AC driving is just to shift the
broadens also the this step over of the Fermi-Dirac line.
Okay.
Yeah. But we are not injecting net energy. We are just rearranging.
Yeah. This I understood. Yeah. But since the distribution is not like equilibrium, so that will make a change. So
non-equilibrium. Yeah, exactly. Yeah. So yeah. And about the definition of heat, yeah, again, yeah, we are adapting the definition, yeah, which works well for the thermal bath, which we assume that everything is thermalized well deep in the reservoir. So we are calculating the heat deep in the reservoir. So I think we are fine. But anyway, as I told you, the conclusion doesn't depend on the definition of heat, which we're using. Yep.
Okay, Raul.
No, I have a simple question. I have not understood how come that the injection of the AC current doesn't give energy to the electrons.
So actually, yes.
I mean, but you need the AC on, right?
Yeah.
So where does the energy go?
So yeah, it's a great question. Yeah, it's always confuses people. Yeah, I know. And when you apply AC, actually at each moment there is energy going in and out. But I mean, in average, if you average the energy going in and out over one period, it vanishes. That's our finding. So it's like
So that you need energy to keep the AC on,
energy to give AC on.
right? I mean, otherwise,
Well, it's like I don't know. It's like another cost. I mean, for example, so in the example of Scully, for example, you maybe have some cost for preparing bath in superposition. No? Here, yeah. If you want to have some coherence, then you may need another cost that doesn't directly goes into the efficiency. So yeah, it's like analogous to that. Maybe there are some experimental costs to prepare AC voltage, but the AC voltage is not injecting power into the system over a period. So,
but you need more power than if you did not have the AC power. So there is a loss of efficiency because you are wasting more, you are using more energy to produce the same energy through the system.
well, but it's like for me, it's like there becomes more controllability. For example, also they argued that even if there are some costs to prepare coherence, then but you have another degree of freedom, the phase here. So by controlling the phase, you have another knob to control the heat engine. So in our case, also we can tune the AC voltage shape into a lot of different shapes, but that does not directly diminishes the efficiency. So we can use it as another degree of freedom to explore the engines. So yeah.
Okay, more questions online here? No. Okay, so thank you again.
Thank you.
Okay, and see you next week.